the video.
Sorry, we are live now.
Yeah, it's all right.
You can go ahead.
Yes, it is possible, but yes, not advisable. Anyway, so let me introduce Huang today, our speaker. He's working at the Institute of Space Sciences, been here for a while now, working with a group of José Miguel Girard. He's traveling. Yeah. So he studied in Nanning in China, in Guangxi University, and then also did his master thesis in the Kepler Institute for Astronomy and Astrophysics, Beijing, China, and also Guangxi University, I guess a shared program. He stayed for a while also at the Center for Astrophysics, maybe a visit during your PhD, right? You are a CSC fellow from China? No? So you have here written.
Oh, yeah.
CSC
for the PhD program. Yeah.
On the PhD program. Yes. Okay. So your research is on magnetic fields, especially focused on the Orion region. I just took some notes. So you've been leading several efforts like analysis and reduction of the box survey using ALMA. You have been using also the Iron telescope, VLA for the ball survey, for example. And also you had some experience developing some instruments to support high energy physics on space.
Yes.
Okay, when you were in China, I guess, doing your master thesis.
Yeah.
Okay, so as I mentioned, he's been leading several programs at SMA, IRAM, ALMA, and also used the VLA as co-PI with several of people that are here and also at the University of Barcelona. You also code quite a bit, I understand, using Gen4 and do simulations and also
Gen4, yeah.
Gen4. CASA, and then also you are in charge of the work group meetings of star formation group in the Institute and the University of Barcelona. Some of them are here, I guess. Yes, and then you have quite a few some papers from your PhD already, so mostly on magnetized stars and the Orion region, which is what you are going to tell us today. And I understand that you are going to finish your PhD soon.
Yeah.
So congratulations for that. And then the floor is yours.
Okay. Thanks, Julian, for your kind introduction. And I'm Huang, and I'm the last year PhD student and working at the star formation group at the institute. And I'm working on magnetic field and star formation. Basically using the observational data to study the role of magnetic field on several hundreds to 1,000 CU scale. So I'm also working with like Aurora, Chema, and here I'm going to introduce my work I have done during my PhD. So here is the outline. Here is the outline, and I will follow the outlines and firstly give a brief introduction of the background of magnetic field and star formation. And then I will introduce the specific work based on the observational data. So the first thing have been on my mind is that how do stars form? Well, first of all, where do they form? Here you can see a spiral, based on picture of spiral galaxy, and you can see actually the stars are formed inside the large molecular cloud, and these dark lanes and these huge structures within full of plasma gas. Actually, this is not our galaxy, and we should move to the next slide and crash into the hadron. So here you can see a nice imagery of our galaxy, and you can still see the dark lanes here, but now from our perspective, and the stars are forming inside these huge structures. And here you can see the scale bar here, which is scaled to the sort of nearby star forming region. And that is Orion, one of our famous star forming region, and they can form the individual objects themselves are much smaller in size, of about few tens a year. So this is an incredible multi-scale process of has so many questions that we should answer all the way from the scale for entire galaxy, or even beyond actually, and down to the scales of individual forming stars and dips. So here is a scale-free picture to show the process of star formation. On the upper left, you have here is a giant molecular cloud, and as you move clockwise down to the right, here's a molecular clump, which is a dense region within the cloud. And then you get a protostellar core where one or maybe a few stars are going to be forming. And then down to the protoplanetary disk. And finally, the solar system, after all the dust and gas has been blown away or accreted. So there are so many questions that we can ask. What do those molecular clouds look like? How do they form such structures that we see, as it turns out, quite filamentary and elongated? And once you get down to the protostellar core, what does how do those stars accrete their material for other irradiation conditions of protostellar core? And for people who really care about this, how does the magnetic field look like? How strong is it, and what is it doing inside the disks themselves? Because people have known theoretically for decades that magnetic field is really essential for the formation of structures within disks. It can even affect the migration of planets. It can affect the ultimate formation of the planet's system through some mechanisms like magnetic braking. So the magnetic field and polarization is very essential for these questions. But how to trace the magnetic field? So here you can, the main observational way to is by detecting the radiation, the polarized radiation of the region we observe. If we observe at millimeter or sub-millimeter wavelengths, we will observe the dust thermal emission. This emission will present an electric field that will oscillate along in the direction of the major axis of the dust grain, and thus it is linear polarized, but parallel to the dust grain major axis, and thus perpendicular to the magnetic field. So the most common theory to explain this alignment between the dust grain and magnetic field is called radiative alignment torque. That's the grains can be aligned by torques conveyed by the local radiation field. So here you can see the cartoon field, the cartoon grains, which have already aligned by the Billet's mechanism, and they can typically emit the polarization more strongly along their long axis than along their short axis. So you detect this orientation, and to infer the magnetic field, you should take this orientation and rotate it by 90 degrees. So that's what we are going to be seeing the most of the talk. So once we get down, get deeper in to the scales of disks, the polarization would be produced by dust scattering. This is independent of the magnetic field. So here you can see if there is a line, unpolarized line, hits and dust grain, the resulting scattering signature would be polarized, depending on the angle at which it is polarized. It is scattered. this happens because the dark square acts like a dipole oscillator, which can only emit the radiation perpendicular to the direction of the incident light. So this is Rayleigh scattering, and it says that if we observe along the direction, in the backward or forward direction of the light, the scattered line appears completely unpolarized. But as the angle increases, the scattered line becomes more polarized. So the idea for the disk, we should see the radial polarization in the inner ring because the radiation is partially polarized in the direction along the radiation field, along the anisotropic radiation field. This anisotropic radiation field from the inner region. And we can see the azimuthal polarization because the incident light incident lights are coming from the scattering. So this is called self-scattering for the outer region. So the idea for this is based on a picture, and for the inclined disk, we will see the polarization vectors should be aligned with the minor axis of the disk. So for the role of magnetic field, if we look at the linear polarized integral convolution map from Planck curvature, at large scale magnetic field is comparing this dust map with the magnetic field inferred from dust polarization. Magnetic field is actually doing something important at a very large scale. So here you can see the drapery here, which is indicative of magnetic field. So the color scale here is the column density. So in the magnetic field in lower density region, like here or here, something like that, it's preferentially aligned with the elementary structure. In dense region, the magnetic field in dense region, probably something here, tend to be perpendicular to the filament axis. So the conclusion was that at large scale, magnetic field is dynamically important. And what about on small scale, like few tens AU scale, few hundred AU to few thousand AU scale? Actually, core magnetic field is always misaligned with the envelope magnetic field. At small scale, magnetic field always shape, in some cases, shape hourglass structure due to jacking on field lines by infalling flux frozen material. But many protostellar sources have a more complex morphology. You will see in the next slides. And in some observational study, the magnetic field is misaligned with the outflow, both in low mass and high mass dopamine region. However, these studies, the sample in these observational studies are in different evolutionary stages and observe with different observational spatial resolutions and located in different dopamine regions, which could greatly affect the results of the magnetic field. So to address this issue, requires a survey of source in a single region that has typical dopamine conditions. Orion may be the best region to study it for this study because Orion has is more has different star forming conditions, and it's the closest massive star forming region is about 400 parsecs away from Earth, and it's a very well studied part of a large molecular cloud complex, and also has the largest population of star class 0 protostars within 500 parsecs. Most solar-type stars are likely found in high-mass star forming region, making Orion more typical representation of star forming conditions within the galaxy. So the B-field Orion protostellar survey was proposed to observe 870 micron dust polarization toward 57 fields with the scale of 400 to 2000 EU. At these scales, the observation can trace the magnetic field uniformly toward the young protostar, around the protostar. So the observation was made in 2019 and with the resolution of about 1 arcsecond. And here you can see the continuous spectral sector, CO322 and C1703C22 are the main molecular lines used in this study. CO322 used to trace the outflow structure, while C17 trace the velocity field in this gas. So next, here is one of the study based on the observational data. So here you can see the result after data reduction. We found 7 sources with very compact polarized emission. That means the region with maximum of polarization intensity peak is length less than the disk size. It is the emission, the polarization emission are coming from thought to be coming from disk. So in the first panel, the color scale is the polarization intensity, and the red and blue counter are the outflow, and black counter indicates the total intensity. In the second panel, here you can see the color scale presents the velocity field, and red and blue arrows indicates the mean direction of the outflow, and the magenta segments indicates the polarization. And the third panel is the zoom-in version of the second panel. So here you can see it's very compact. And for other source with more extended polarized emission, we think that the polarization is mainly coming from the envelope. So in this case, you can see the similar plot as and on the difference is the vectors here, the gray vector, which is indicative of magnetic field, which is the polarization rotated by 90 degrees. So you can see here the magnetic field shape a standard hourglass, which is in with the field lines pinch inward and expanding outward. And the rotated hourglass here, which is have similar structure as the standard hourglass, but repeat by 90 degrees with its axis perpendicular to the outflow. And the spiral one and complex and very complex magnetic field morphology, and do not have enough polarization data. to identify the magnetic field structure. So here you can see a brief summary here. We find 8 source exhibit standard hourglass structure, 13 source have a rotated hourglass structure, and 9 source shows the spiral configuration. And we think that because for more than a decade, one of the primary ways to have tested the importance of the magnetic field in star formation region have been via comparison of several acids, like the magnetic field acids, the outflow acids, and the rotational acids of the protostellar disk. This is because if a protostellar core is very strongly magnetized, the magnetic field has the ability to align all the relevant acids. This happens because the magnetic field magnetic braking phenomena, where a strong magnetic field removes the angular momentum from the central source and causes the angular momentum and magnetic axis to be aligned. So to estimate this the direction of these parameters, so we can first is the outflow. So to estimate it, we connect the measure its position angle by the follow by these steps. So you can see a little bit, but connect the source center and this edge region, and take the bisector of the open angle, like the arrow of the blue sheet outflow and the arrow of the red outflow, and then finally take the average of the red sheet of blue sheet position angles as the outflow direction. So take the average of the blue arrow and red arrow as the outflow direction. And for the magnetic field acids, we first follow to perform the total intensity weighted method to give more weight to the magnetic field to the mean direction in higher density region. And we also to make a comparison, we also perform the error, the uncertainty weighted for the polarization angle to give a wedge weight for each point for each pixel. So after the weighted polarization angle should be rotated by 90 degrees to infer the magnetic field mean direction. And for the disk, the orientation, this is a diagram to show how to estimate it. And we take the disk orientation from VANDAM observation, which has higher resolution. So let's see the first result for the relative alignment. So here you can see the x-axis is the difference between the outflow and polarization. And the y-axis is the counting number of source. And in the right panel, the x-axis is the disk orientation along the major axis, and the polarization is the difference. So we check that for these 17 compact source with compact polarization emission, we find most of them have their outflow aligned parallel to the polarization and perpendicular to the disk orientation along the major axis. So which is the one of the signature of cell scattering. So we can see here the disorientation along the major axis would be along this direction. And we can find this very consistent. And we also check the fractional polarization and the dust opacity for this source, which is also consistent with the cell scattering. So this potential cell scattering signature suggests that because the source is at a very young protostar phase, most of them are class 0. So this potential cell scattering signature suggests that the grain growth has already occurred at a very early stage of protostar phase. And for the other source with extended polarized emission, it is the polarization is mainly coming from the envelope. We can find that 40%. Here you can see a similar histogram here, and the x-axis is the difference between outflow and magnetic field, both of them. And we can find this one, there are 40% of the source have exhibit the trend that magnetic field is perpendicular to the outflow. This means this suggests that the magnetic field may play a significant role in setting the angular momentum within of embedded envelopes and outflow. So we also find that the source, 14 source protostars have a significant velocity gradient. So we fit 2D linear regression fit to the Bowen-1 map within 1000 AU and to estimate the velocity gradient direction. And we divided this 14 source into two types. One is the perpendicular to the outflow. The other is not perpendicular to the outflow. So this classification because avoiding because of the outflow may also affect the velocity gradient. So the per type here means the magnetic field. The velocity gradient is less affected by the outflow. So let's focus on the per type here. So this A source we can see is have very significant velocity gradient, which is also less affected by the outflow. And we can see these A source are almost perpendicular. The magnetic field are almost perpendicular to the outflow and parallel to the disorientation along the major axis. So a significant velocity gradient is always associated with the location. This correction reveals a potential link between the kinetic and the magnetic energy at envelope scale. And here, because the angle observed is projected onto the plane of the sky. So to study the influence of the projection effect, we plot the CDF function for the observed angle and compare it with 2D simulation intersection angles uniform projected. to the model, comparing to the model. So you can see both the random and perpendicular model. And from the KS test, we can see the random and perpendicular model would be possible for this distribution from 3D perspective. And come to the next work. It's the fragmentation and the role of magnetic field in fragmentation and disk formation. So the dense cores with some angular momentum are prone to fragment into multiple projects. Since dense cores or molecular clouds are always rotating, so there should be some mechanisms to reduce the fragmentation to the observed levels. Some studies suggest that the turbulence and magnetic fields would be the factor to suppress the fragmentation. Like for instance, the turbulence, the compression turbulence will promote the fragmentation, while the solenoidal turbulence will suppress the fragmentation. And for the magnetic field, we also suppress the fragmentation because it will provide support against the gravity collapse, and also the magnetic braking, which carries away the angular momentum from the inner region of the disk of the core. So to estimate the fragmentation level, to test these two vector parameters, the influence of these two parameters on the fragmentation, we first should estimate the fragmentation level. So this is defined as a number of millimeter sources inside a selected region, and the sources should be within the regions with more than 10 sigma intensity. So the color scale here is the region with the 10 sigma intensity larger than 10 sigma. So the source here are identified from higher observational data of VANDAM project. So here in the inner region, we can see there is a star here. So we'll count the fragmentation level as 1 for this region, and for the annular region between the black dashed circle and blue dashed circle, there are 2 stars allocated here, but with less weighting. So for these 2, we will give also 1. We will count also 1 fragmentation level for this region, and for the outer region, we also give a less value of 0.25. So the fragmentation level for this source would be 2.25. Here the region is like is the typical scale of the envelope, so it should be reasonable. So let's do the correlation here. So the x-axis is the fragmentation level. The y-axis is the non-thermal velocity, which is also indicative for the turbulence energy. So we performed 3, maybe 2 Pearson linear correlation coefficient here, and the Spearman's rank correlation coefficient here, and also the p-value to test the this correlation is significant or not. So when this statistical test, we do not find any correlation between the fragmentation level and the turbulent, the non-thermal velocity dispersion. But we do find some correlation between the fragmentation level and the polarization position angle dispersion. So we can see, and the position angle of the magnetic field is inversely proportional to the magnetic field strength. So this correlation means the envelope fragmentation tends to be suppressed by the magnetic field, so which is consistent to the theory predicted. And for the magnetic braking and disk formation, so firstly, I would like to introduce the magnetic braking signature. So if you have during the collapsing phase, the magnetic field lines are drawn inward into a very pinch geometry. So this pinch geometry of the magnetic field will strengthen the field strength. It carries away the angular momentum. This phenomenon called magnetic braking, which could how to say, efficiently reduce the angular momentum and suppress the formation of the supported disk. So if this phenomenon is very strong, we cannot see any disk. There are some theory to have been proposed to reduce the magnetic braking. One of them is that the misalignment between the magnetic field and outflow. So let's test it. This is the misalignment between the magnetic field and outflow, and the y-axis is the disk radius, and this is the disk mass. So we can see a very strong correlation. That means if the magnetic field and if how to say, if the magnetic field and outflow have a larger angle, and you will get a larger disk. This also yeah, and also if we remove this point, because this is how to say, will be affect the correlation here. If we remove this point or this point, and the significant the correlation is also significant. We already tested that. So this means that the misalignment between the magnetic field and outflow would weaken the magnetic braking, allowing larger disk formation. So which is consistent with the theory predict. And other things, and next work is let's back to the brief summary. Okay, I'm going to finish really fast. And let's see here, you can see, which already shown. Here is a per type, which means the have very strong velocity gradient, and only of time means the velocity gradient is very big. So we can see all the standard hourglass have a very big velocity gradient, but rotated hourglass and spiral have, most of them have very significant velocity gradient. That should means This suggests that the different magnetic structure, magnetic field structure, may indicate some relationship between the magnetic field relative to turbulence and gravity. So as such, it is necessary to constrain the magnitude of the magnetic field. So to estimate the magnetic field strength, we follow like DCF method, which is the original form for the DCF method. But this method only reliable for the cases with this angle dispersion lower than 25 degrees. So there are some methods to improve the reliability for the estimation, like Hayes method and Fazettas method. So we use these two methods to estimate the magnetic field strength for the source with extended polarized emission. So we can find that our standard hourglass field has more strong, the magnetic field strength is more significant. And for other fields, magnetic field structure, the magnetic field strength is much lower, maybe 2 times lower than this one. Okay, briefly, let's come to the conclusion. It's really fast. And during my PhD, I have the work I've done is identify several magnetic field morphologies, and we also find that self-scattering signature at a very young protostars, and this means that the grain growth has already occurred at very early stages of the stellar phase, and we also find 40% of protostars exhibit a mean direction of magnetic field is perpendicular to the outflow. This suggests that the magnetic field play a role in setting the angular momentum of embedded envelopes and dips and outflows. And we also find fragmentation level is positively correlated with the polarization angle dispersion. And this means that the fragmentation is suppressed by the magnetic field. And also we found a very strong correlation between the dip size and magnetic field and outflow alignment. That means that this alignment will, the larger angle of this alignment will weaken the magnetic braking signature, allowing a larger dips formation. And finally, the field strength for a standard hourglass structure is more significant, and 2 milligauss would be necessary to maintain such structure at envelope scale. So this is work I have done, and thank you for your attention.
You're good with taking time. No problem. Okay, so question for both. I have questions. But I got one. Thanks for the note. When discussing the sources that have the compact magnetic field, that would be the self-scattering one, there is one source, I think it was called 250, so that does not seem to follow this.
Yeah, so we remove that case for the analysis. So we can't this source the polarization is produced by the magnetically dark square alignment.
So it could not be self-scattering.
Yeah.
Yeah, that's a question for you. So you are talking about these magnetic fields. So I understand these magnetic fields are extrinsic to your region. So this is the galactic magnetic field that goes into Orion, or is some locally produced magnetic field by the protostar, or where's this magnetic field coming from?
It's the ambient magnetic field, but how do they come from? I have no idea. Maybe they're already there. or
But this is extrinsic, so it comes. This is basically following the galactic magnetic fields that you see there. That's the idea.
maybe, but how to say? I'd say maybe or maybe not, because the magnetic field in a large scale, if the magnetic field is very strong, the large scale magnetic field will align with the angular magnetic field. But if the magnetic field is very weak, they will misalign. And how do they count from?
I always got fascinated by these galactic magnetic fields also. So
Okay.
yeah, I don't know what to expect. So,
I think it should. I would say it's connected to the large dynamics of the galaxy. With the largest scale is magnetic field, and then when you go into the clouds, so then the orientation and everything can change. Because we have a lot of turbulence, rotation that can shape the magnetic field. But my understanding is that it will be connected to the large scale.
Oh yeah.
the continuation of the large scale, like when we're going to a plasma or something, it starts to get more exact.
This is the way
Things. Would you say then that, if I understood correctly, at the end, when you end up with your star and planet, for example, planetary system form, the planetary system would be aligned then to kind of the perpendicular magnetic field. So the result, because if you have a disk, at the end, the planetary system ends up aligned for planets with this, right? So planetary systems should be kind of following the magnetic field.
Sorry, what?
So you have your magnetic field that influences how you form your disk, right? And you have your magnetic field, and then at the end, this angular momentum remains, of course. You will end up with the planetary system, which is basically your original disk that got coagulated into planets. So would you say that then planetary systems that are a result of this are going to be aligned with this initial magnetic field?
For finally?
No, for planetary systems.
Planetary system. Okay. I didn't get the point. Maybe we can discuss later.
Yeah, well, this is a long question.
I think it makes sense, the conclusion that we have, because basically what you say is that the misalignment is connected with this. So, for example, regarding exoplanets, we have found that most of the misaligned exoplanets have been found around more massive stars that cannot generate angular like momentum braking that easy. So that conclusion, I think it makes sense with the fact that we find more that we found aligned planets around stars with like less massive stars.
We can discuss it. This is a long-standing question. I mean, if you have your galaxy rotating like this, and you have stars forming, so there's some angular momentum over time, right? On average, you have an angular momentum on the plane of the galaxy. So you may expect, if there was no magnetic field, you may expect planetary systems, even binary stars, to be kind of aligned with this angular momentum of the galaxy of the Milky Way, on average, of distribution. But this is not observed at all. So it's uniform distribution. And then, of course, if the magnetic field is so convoluted and it's actually affecting the actual planet formation at micro scale, that could be one of the reasons why. This is why I'm coming from it all. So it's, yeah, and then it's related to how the planetary systems get aligned. The star and the planetary system. I mean, the sun doesn't have a lot of angular momentum anyway, compared to Jupiter. Any other question? Okay. How massive are these stars?
It's about
Or is it
several. It's a low mass star, like several solar mass.
Low mass.
Up to several mass. 2 or 3 solid mass.
Okay, 3, 4 solid mass.
For envelope mass.
Okay. Well, thank you very much. Downstairs, please wait for the speaker for starting with